So we're in section 13.8, and today we're going to talk about today we're talking about relative extrema. And we've mentioned it briefly as we did a few things throughout the chapter. So when we had a single variable function, the extreme value theorem tells us that a continuous function always obtains a maximum or minimum on a closed interval. We have a similar thing for multivariable functions. So when we have a continuous function, we'll have a minimum value at least one point and a maximum value at least one point in a closed bounded region. And closed bounded region means closed means it contains its boundary, and bounded means it's a subset of a larger region. So we're taking some subset of our domain and saying that our function is going to obtain a maximum or minimum value in that region. So let's just define what we're talking about with a local maximum or minimum. It's pretty intuitive, but I just want to make sure we have our definition. And then we'll talk about how we find them. So we have a f of xy as a local maximum. If f of xy, and I'm going to say at point AB, if f of xy is less than or equal to f of AB, for all xy in some open disk around AB. So it's just like you would think of it. It just means that our function is bigger than all the values around it. And we say some open disk because we're just talking about the local behavior. We're not talking about an absolute maximum here. We're saying in this region, this is the maximum. This is a maximum of the function. And we just switch our inequality around for a local minimum. So f of xy is a local minimum at this point. If our function is greater than the value at AB. In some region around the point AB. So that's all we're talking about, just our intuitive idea of a local maximum or a local minimum. And this tells us how the function, the value of the function, compares to nearby points. That's all we're talking about is what it compares to close to or nearby. We're not talking about over a large region. We're talking about nearby. And we have a critical point. Just like when we're talking about single variable functions, we're interested in critical points of f of xy. So f of xy has a critical point. And we've talked about this before. At our point AB if f sub x of AB and f sub y, I'll say equals f sub y of AB, and this equals 0. So when our first partials equals 0, we have a critical point. Or if f sub x AB or f sub y don't exist. So this is how we find our critical points. We talked about this before. If we have our first partials equal to 0, that's going to be a critical point. If our first partials don't exist, that gives us a critical point as well. We can prove that relative maxima, we're not going to do it, but we can prove that relative extrema occur only at critical points. So that's going to be our key idea. So we're looking for our relative extrema at our critical points. And like we talked about yesterday, if f sub x and f sub y are both 0, then our gradient at AB equals 0I plus 0J. So every directional derivative at AB is 0. And so that tells us that our tangent plane at AB is horizontal. So just like we talked about yesterday, just like in single variable calculus, when we're at a maximum or minimum, relative max or relative minimum, our tangent line is horizontal. At a relative extrema of a multivariable function, our tangent plane is horizontal. When I forgot our little symbol here, didn't I?
Diamond. Yeah, when you write that in there.
Mm-hmm. So our tangent plane is horizontal. So let's look at a couple of examples of finding extrema. So this is, hopefully this is a little less definitions and concepts and a little more kind of actually calculating things. So let's look at the first one. Any questions before we go on? All right. So for this first one, we're going to say that g of xy is 9 minus x minus 3 squared minus y minus 2 squared. And we want to find relative extrema for this function. Now, before we start calculating, before we start using our partial derivatives, I'm gonna borrow a line from your book from last year.
Clever.
Let's be clever.
No.
So let's look at this function. Look at the form of the function. What is the largest value this function can take?
11.
John says 9. Because we're subtracting here, and anything that we put in for x and y, we're going to be subtracting a larger number. So for any x and y that's x and y greater than 0. What's that?
Well, if x and y were less than 0, we would still square.
Right, we're squaring, we're making a larger number, so we're going to be subtracting something from 9. So for any x and y, the largest value is when x equals 3 and y equals 2, because then we're subtracting 0. So the largest value is going to be when we have at our point 3, 2. Anything other than that is going to be smaller. So our maximum is going to be f of x, y equals 9. So that's going to be our extrema. So we have a maximum g of x, y equals g of 3, 2, and that's going to be 9. Now, if our function doesn't behave nicely like this and kind of submit to being clever, we have to use some other tools. So we know that our extrema occur at critical points, but critical points don't always give us an extrema, right? We can have inflection points. Same thing happens with multivariable functions. Rather than inflection points, we can have saddle points. So we need to figure out if we have an extrema, if we have a maximum or minimum, or if we have a saddle point. So we can have saddle points. At critical points. Rather than extrema. So we need to figure out how to determine if we have an extrema or if we have a saddle point. So with single variable functions, how did we do that? What's that? Take the derivative, so that's how we find our critical points. But the second derivative, so we had the second derivative test, right? And that told us something about the behavior, what type of point the critical point was. So we have something similar with multivariable functions, but rather than the second derivative test, we have the second partials test. And it's a little more complicated than the second derivative test. So we use the second partials test. And we're just going to state it. We're not going to try to prove it in any way. So we're assuming that our function has continuous second partials. Oh, they didn't want to talk to me. All right. My office phone does that all the time too. It'll ring once and then.
You should try to answer it really fast. Just get it. Hello.
So f of x, y has continuous second partials in an open disk. About the point that we're interested in. So our function is behaving nicely. And we know that our first partials are equal to 0 at our point. So we have a critical point. We have a well-behaved function. So we want to figure out if we have a saddle point, if we have a maximum, if we have a minimum. So we're going to let D, and we can call it the discriminant, kind of like the discriminant for the quadratic formula. D is going to be, we're going to say that's f sub x at AB times f sub y at AB minus f sub xy at AB squared. So that's our discriminant. This is what we're going to use for our second partial test. We have four conditions for our second partial test. One, if d is greater than 0 and f sub xx is greater than 0, then f of AB is a relative minimum. Our second condition, if d is greater than 0, and f sub xx is less than 0. Then our point is a relative maximum. Our third condition, if d is less than 0, then we have a saddle point. And finally, our fourth condition, if d equals 0, we can draw no conclusion. And we would have to do some additional work. So this is our second partials test. This is how we determine if we have a relative maximum, a relative minimum, or a saddle point. All having to do with our various second partials. So let's do a quick example, finding relative extrema of a function. Everybody good with this? Pretty straightforward, very similar to what we've done before, and it just involves a lot of calculation. All right, so our example, we have f of xy equals 2xy minus 1/2 x to the 4th plus y to the 4th plus 1. And we want to find relative extrema. So first we need to determine our critical points. We need to find our critical points. And we need our first partials for that. So our partial f sub x is going to be 2y minus 2x to the 3rd. And our partial with respect to y, f sub y, is going to be 2x minus 2y to the 3rd. So we have critical points at, these both equal 0 at 0, 0, so that's the first critical point. So we know we have a critical point at 0, 0. And we can tell that just by looking at our functions. So 0, 0 is one critical point. And we need to solve simultaneous equations to find our other critical points. And our other critical point happens at plus or minus 1, 1. Plus or minus 1, 1. We could and we find that what I did to find this is I solved one equation for one variable and substituted and solved the other one. So you can go through and solve simultaneous equations. Determine that your other critical points are 1, 1, and -1, -1. Does that make sense? Okay. So I won't go through the process of finding critical points. Sometimes, depending on your function, if your function is really complicated and your first partials are really complicated, finding the critical points can be a little tricky. But you guys know how to do that. So these are our critical points. Now we need to determine if we have a maximum, a minimum, or a saddle point. So let's use our second partials test. So we'll calculate our second partial derivatives, f sub xx. Second partial of x with respect to x is just minus 6x squared. F sub yy is going to be minus 6y squared. And f sub xy is just going to be 2. So there are our second partials. And we just need to calculate our discriminant. So f of, we'll look at 1, 1. That's what I want to do. F of second partial of f at when x equals 1 is just minus 6. Second partial of y when y equals 1 is minus 6. And this would be, we can say the same, this is for plus or minus 1. Because we have an x squared and a y squared. So we have a minus 6 for our second partials, and our f sub xy is always 2. So for our points plus or minus 1, so our discriminant gives me minus 6 times minus 6 minus 2 squared, and that is greater than 0. So our points, our discriminant is greater than 0. Our first partial is less than 0, so we have a relative maximum at 1, 1, and minus 1, minus 1. So there's our test for 1, 1, and minus 1, minus 1. And I'm just going to write this up here to remind us that that's what we did here. And for 0, 0, our other point, our discriminant is 0 minus 2 squared. Each of these evaluate to 0 at x and y equals 0, which is less than 0. So we have a saddle point. So let's take a look at what this function looks like if we graph it out. So I have it graphed here. I think it is this one. So I had a hard time getting a good graph of this function. No, that's the wrong one. It is this one. There we go. So if we look at it from the side, there are two maximums at this point here and this point here. And our saddle point, you can see right in the middle there. It had a really hard time. Anything I tried to graph this with had a hard time graphing that saddle point. But that saddle point is right in the middle there. And it gets a little better with all the lines drawn in here. So our maximums are here and here, and inside here we have a little saddle point, kind of between those two peaks. Now, and again, I wanted to remind you about this, the CU, the Mathematical Visualization Toolkit, something that's available online if you want to look at graphs of these functions to have an idea of what you're working with. You can always access that just online. You don't have to download anything. I just Googled CU MVT and to get this, and it'll plot these 3D functions, and it works pretty nicely. I tried to do it with Mathematica, and for this function, Mathematica would just give me a plot that looked just like a kind of a curved tabletop. It just looked like this. So it wasn't getting the peaks or the saddle point at all. So this one, it does work pretty nicely.
So the saddle point is just where it dips down a little between two peaks.
Well, so it would be at a maximum at the 2 peaks. It would go down to the saddle point in the middle, and then at the saddle point going at 90 degrees to if we went straight down, like the maximum directional derivative from the peaks, it would go straight down, and then at that point, if you're going 90 degrees to that direction, you'd be going downhill again. Does that make sense? So it's like the hyperbolic paraboloid, where you have they come down this way and then it goes down that way from right in the middle. So that's what that point would look like if we could get a good plot of it. So it shows it kind of flat in there. If we look at it from the side, it shows it kind of flat. But from that point, right there in the middle, it's curving, it's going downhill this way and downhill down the back side of that thing. Okay? All right. So there's our second partials test, our way of determining relative maxima and minima. On Monday, we'll talk about how we find absolute maxima and minima. And when we talk about absolute maxima and minima, we have to look at our function on a bounded region, because our function could take the absolute value, or take a maximum value on the boundary of the region. Just like in single variable calculus, you had to look at the endpoints of your domain to see if you have a maximum at the endpoints. Questions? All right. Homework. You guys, what do we have, 4 days now? No. These problems can take, because there's a lot of calculation involved, they can be a little long, so there's not a lot. All right, there you go.